So the first uranium enrichment method that we're going to take a look at is something called electromagnetic isotope separation, or EMIS. Now, the physics and engineering behind EMIS, it's about as basic as you can get for all of these different enrichment methods. It requires pretty much the least amount of knowledge, and the technology that you need to engineer one of these things is basically has the lowest bar of entry. The technology is widely available, and it's nothing that's extremely hard to set up. Now, EMIS does have its drawbacks, don't get me wrong, but usually if we were talking about a proliferant nation, this may be the first thing that they try. So let's take a look at it. Before we get into the particulars, let's talk about where this was used. Now, as far as I know, the only country that ever used EMIS on a large scale for uranium enrichment was the United States during the Manhattan Project. And they built several of these devices, and we'll talk about what they actually are here on the next slide. They built several different types of these devices, and they housed them all at Oak Ridge National Laboratories. Now, they had two different types which have two different physical characteristics. The first was called the alpha, and they're called calutrons, and I'll explain in a second why they're called that. And it went from almost natural uranium. So instead of 0.71, it started at about 0.9%. It took that feed at that percentage and brought it all the way up to 15%. They then took the 15% enriched material, and then they fed it through the second, or the beta unit, and that went from 15% all the way up to about 90%, so up to weapons grade. Now, the radius of curvature are going to be different on these, and again, we'll see why. And the number of stages that they used was also different between them, 96 versus 36. Now, this was the first. Well, it wasn't actually the first thing we tried. There was thermal diffusion that went from the natural uranium up to that 0.9%. But this was kind of one of the first technologies that we implemented in order to make sure that we could get enough uranium enriched to a level that we could use in a weapon, before either the Nazis or the Japanese got it. And there's some pictures here. One shows the Alpha racetrack and the so-called tank, which is basically where you either, and I'm not really sure what this is referring to. This is either referring to where you put the stuff you started with or where you collected the stuff you ended with. Now, if it's so old and nobody's used this outside the US on any kind of large scale, why are we even interested? Well, again, that low bar of entry for a would-be proliferator means that, again, this may be the very first thing that any of them look at. And so I don't know how many of you remember, but the whole reason we went into Iraq, because they were suspected of having weapons of mass destruction and including a program to enrich uranium. They did have sort of a nascent program, and the route that they ended up looking at was EMIS, because again, the technology is readily available and it doesn't require a huge amount of investment on the part of a proliferator. So this design that we used in Oak Ridge, it's so basic that literally almost anybody could replicate it if they had the resources. And this is a problem, and so we need to know about EMIS and how it would be implemented. So how does it work? Well, basically, in theory, if you had, say, different isotopes. So say I had an atom of uranium-235 and an atom of uranium-238. Now, if I accelerated those along a curved track or along a straight track, and I applied a specific magnetic field to them, if they had the same charge, so they were both missing either one electron or two electrons or three electrons, both the same. So if they had the same charge moving through the same magnetic field, right, the amount that they would curve going through that magnetic field would be different. And because it's based on their mass. And it also has to do with their velocity at the same energy. So because that curvature is different, we can figure out where to put our little buckets that we're going to collect either our uranium-235 or our uranium-238. Now, in a perfect world, if everything went exactly as it did in the theoretical model, we could get 100% perfect separation between our uranium-235 and our uranium-238. Now, I said in a perfect world, it doesn't actually happen that way. One of the main issues is that while moving through the magnetic field, or even just looking at what their ionization state is or how many electrons that they're missing, there is some variability in that. We can't do it perfectly 100% of the time. So that maybe one of our uranium-235s has missing 3 electrons, so it's got a +3 charge. But the 235 has a +2 charge, or the 238 has a +2 charge, as long as they're different. And then the force that's being enacted upon them is dependent upon physical things like the strength of the magnetic field, which relies on the magnets. And the magnetic field has to be so high that they're using electromagnets. So that means is the same amount of current going through all of the electromagnetics to produce a perfectly uniform magnetic field? Are they spaced the correct distance apart to provide that uniform electromagnetic field? And the answer is probably not. So there's going to be some variation on that radius of curvature that we're expecting. So it's not going to be perfect. Additionally, because it's not perfect, we're still going to collect at those buckets that we set up, but we're going to have some that are smashing into the walls before they get to the buckets, or they're never going to hit the buckets because their radius of curvatures isn't quite there. So they're going to overshoot it by quite a bit. Okay, so it's not perfect, which is why we had different numbers of stages for that legacy system that we built for the Manhattan Project. If it was a perfect world, there'd be one stage of alpha and one stage of beta. Now, the name Calutron, some of you may or may not be familiar with it and where it comes from. Well, if we take charged particles like our ionized atoms and we move them around in a curved path, that thing that's doing that is now something called a cyclotron. And Calutron is sort of a portmanteau between California and cyclotron, because the ones that were involved, the cyclotrons that were involved in the Manhattan Project, were all designed by one particular guy, Ernst Lawrence, and he made a bunch of them, and he was out in California where Livermore National Labs will be from his point of view. So when they were looking at these things, it's just another California cyclotron. And so they took that, mashed it up, and the name Calutron stuck. But it is kind of specific to just those involved in the Manhattan Project, but the name is kind of stuck around. So we have where the material that we're starting with goes here. This is where we're going to ionize it. We're going to strip those electrons off. We have our paths, and we have our 2 different buckets. So we can actually calculate what that radius of curvature is in order to figure out where we need to put our buckets. And it's dependent upon a couple of things. So if we look here, this is a much more simplified diagram than the one we saw in the previous slide. So if we look here, the force exerted on a charged particle moving through a magnetic field, it's proportional to the charge on that whatever that atom is. It's also proportional to how fast it's moving, or its velocity, and the strength of the magnetic field. Now, for those of you that have seen cross products and dot products over the years that you may remember from algebra, maybe not, this is simply a cross product between the ion velocity and the magnitude of the magnetic field. Now, if we're not looking at what direction it's going in, we assume it's going in the direction we want, we can kind of simplify that. And we can say that the force that's being exacted or exerted on that ionized atom is going to be the mass times the velocity squared over r, which is the radius of curvature. And this from a cross product turns into a simple dot product, and we end up with the charge. So how much was it ionized, its velocity, and the strength of the magnetic field. A little bit of algebra, and we can find out that the radius of curvature, if all of these, everything being equal, we can find out the radius of curvature using those particular parameters. Now the mass we can figure out, it's just, the atomic mass. So the A number of whatever we're using, so counting protons and neutrons. So that's pretty straightforward. We have 235, we have 238. We have Q, so what's the charge on it? We're going to, again, although it is variable in real life, we're going to set that to either 1 or 2 or 3, depending on how many electrons we think we're going to strip off of them most of the time. And B is the magnetic field, and that's also something that we can set, that we can determine beforehand. Now, the only thing that looks a little bit more difficult to figure out is this V term, or the velocity term. So this comes from something called the work energy theorem. Now, some of you may have had college physics, and you'll probably remember the formula for kinetic energy, which is 1/2 mv squared. So 1/2 times the mass times the squared velocity. And that's equal to how much kinetic energy it has. Now, we can use this formula to solve for the velocity. Now, for charged particles, when we're talking about ions or electrons, the kinetic energy is represented usually in terms of basically how much did we accelerate it through a voltage potential. So if we took an electron and we started it at one plate and it went through the other plate and we applied 10 volts between those two plates, that electron would accelerate and have a kinetic energy of 10 electron volts. And we could do this to 100 electron volts, a kilo electron volt, mega electron volts. And it's the same with these ions, these uranium ions that we're going to be looking to separate. So if we know how much we're accelerating these things, say both our uranium-235 and 238 are going through a potential of 100 kilovolts, which means they'll have a kinetic energy of 100 keV, we can plug that number in for the kinetic energy. We know the mass. We can solve for the velocity. And then we can then take that number and we can put it into this top equation. So mass, velocity, charge, and magnetic field. And from that, we can figure out, everything else being set, what is going to be the radius of curvature for these charged particles at this particular kinetic energy moving through, with this charge, moving through this magnetic field. Basically, where do we put our buckets? That's all that this is telling us. And down here at the bottom, I figured I'd go ahead and give you these conversion quantities because one of the important things anytime you do a calculation like this is to make sure that all the units line up. So in this case, I'm giving you the conversion from kilo-electron volts to joules, and then 100 kilo-electron volt, and its joule equivalent. And that's pretty much EMIS. You're just using these parameters that you have control over in order to get as much separation as you want for these different masses. And that's it. So I think the next lesson is going to cover gaseous diffusion, where we're going to see something completely different. It relies more on probability than this does. Now, again, in a perfect world, there's no probability involved in here. Everything should just work and work out perfectly. But because of variability in all of these different engineering designs and these external magnetic fields and so on, there is going to be some probability involved, but it's at such a lower percentage or such a lower factor than it is for something like gaseous diffusion or gaseous centrifuge. We don't use our separation potential, our alpha, to describe EMIS. We instead use our epsilon, or enrichment potential, simply because this, again, theoretically is so much better.